Hello, our project is called BraveEye, and my name is Adam. I'm in charge of the hardware and team lead.
Hi, I'm Faisal Mustafa, and I worked on the LiDAR module for BraveEye.
Hi, my name is Mohammed, and I worked on the thermal module for BraveEye.
Hi, I'm Ryan Pereira, and I worked on the image processing module for BraveEye.
This is what the hardware looks like outside the backpack. This is the Raspberry Pi, which is the brains of the operation. It receives data from our sensors and runs our software, which processes that data. It is powered by this mobile power bank, since all this needs to function on the move. Now here we have our inputs and outputs. This is the LiDAR sensor, this is the thermal sensor, and this is the wearable display. For prototyping purposes, all this is mounted on a bike helmet. The cables are managed with this tubing and fed to this backpack where the Raspberry Pi and power supply are neatly tucked. Now Faisal will explain how the LiDAR functions.
For BraveEye's LiDAR module, we use a 360-degree LiDAR sensor to perform an environmental scan of the firefighter. The YD LiDAR X2 implemented in this project is a low-cost, low-power consuming compact solution for distance measurements of up to 8 meters. This LiDAR unit operates on the principle of laser triangulation. A laser is projected from the transmitter onto the object. The reflected light falls on the receiver at a certain angle. Based on the angle and fixed distance between the transmitter and receiver, the LiDAR calculates the distance to the object. The 360-degree rotation of the motor collects 7 scans per second, with the motor continuously running until a stop scan command is received. The data is communicated with the Pi via a USB to UART adapter, collected in real time and processed by the latest ROS framework, which is ROS Noetic, running on Raspberry OS. ROS provides tools like RViz, which converts laser scans to 2D point clouds for continuously updating visual representation of the distances. This short clip demonstrates the visual we create by customizing MyViz, which is a Python library available in the ROS framework. The firefighter gets a top view of their surroundings as they rotate clockwise. The map updates and rotates in the opposite direction, simultaneously positioning all the forward-facing objects at the top of the map.
Next, Mohammed will explain how the thermal sensor functions.
The basis of the thermal module is an Omron D6T 32L thermal sensor. The sensor works by utilizing a silicon lens to focus infrared rays emitted by objects onto a thermopile sensor. The thermopile sensor converts radiant energy into an electromotive force. Then, a microcontroller and ASIC embedded in the sensor generate an object temperature value from the electromotive force using interpolation techniques and internal lookup tables. Finally, an analog-to-digital conversion is performed, and a digital temperature value is outputted by the sensor over an I2C interface. The D6T 32L sensor consists of 1024 elements arranged in a 32 by 32 grid. The output data stream of the thermal sensor consists of 2051 bytes and is captured by the Raspberry Pi over an I2C bus. A custom module written in Python converts the sensor output data into an array of temperature values and performs signal processing to identify any thermal hazards and possible humans within the sensor field of view. The D6T 32L sensor updates its temperature data every 200 milliseconds, permitting a maximum throughput of 5 frames per second. To minimize the impact of signal processing latency on the sensor throughput, a multi-threaded software approach is being used, wherein a dedicated thread is used to continually read sensor data, and a separate thread is used to execute signal processing operations. Using this approach, the thermal imaging video stream presented to the end user is operating at a variable rate of 4 to 5 frames per second.
Finally, Ryan will explain the software that outputs the image that the user sees through the wearable display.
The image processing module encompasses the reading of data from the thermal module in addition to the implementation of a graphical interface which clearly displays the outputs of both modules. The visual output for the thermal data is written in Python. It receives the temperature data that is updated by the thermal module and converts the 1024 element list into a 32 by 32 array. The array is scaled to 672 by 672 for the cleanest one-to-one image on the 720p viewfind display. Borders to fill the rest of the screen are then injected into the array and set to the value of the average temperature. The resulting array is then converted to a 3D array of RGB values using an appropriate color map, which is then converted to an image.
Now that we've explained how it functions, it's time to demonstrate it.
In this demo, we first see a hotspot warning. The pot of boiling water represents the fire, blocking our firefighter's path, which we can also see in dark red on the thermal display. Our firefighter chooses to withdraw and go a different route. Using the LiDAR sensor, our firefighter is able to make out a doorway despite the smoke obscuring his view. This enables him to see exits in any amount of smoke. A human begins to come into view on the thermal sensor, and a warning for possible human detection is received. Our firefighter gives the victim a high five, signaling a successful rescue mission and the end of our demo.